This is page 96. All right. So we're talking about whether or not a function is differentiable, new word, differentiability, or you could also call it smooth. So if you picture a function, if a function is smooth, we consider it to be differentiable. We've talked about functions that have like a jump right in them, or functions that have maybe go one direction and then they start going a different direction. Neither of those functions are smooth. A function that's smooth would be something like a parabola. There's no corner or like jolt section or something like that. You can follow along it in a very smooth smooth path. So it will have no sharp points or points where the tangent line is vertical. So like a tangent function is not differentiable at certain points because it has vertical tangent lines in it. Tangent looks like this, and it has vertical tangent lines. So we would say it's not differentiable at those vertical tangent lines. An example is a steel roller coaster. If you're on a steel roller coaster and there's a sharp point in it, a place where it's not differentiable, then you're going to go off the tracks, and that could be fatal. All right. Function is differentiable at a point if and only if the derivative at that point exists. And it's differentiable over an interval, meaning from one number to another number, if you can take the derivative for every single point on that interval or between those two numbers. So like tangent is differentiable from here to here, but it's not differentiable on the asymptote. This function up here is differentiable from here to here, but it's not differentiable at that point. A function is differentiable, like the whole function, if and only if the derivative exists for every value of x that's equal to that number in its domain. So like if every single point is differentiable, we say that the function itself is differentiable. Polynomial functions are differentiable. The exponential function is differentiable. Sine and cosine are differentiable. Okay. Since a function that is differentiable at x equals c must be smooth, it must also be continuous. It's not going to be smooth if it's not continuous. So we just learned about continuity. In order for a function to be differentiable, it must also be continuous. I think that's what this blank is. If a function is differentiable, then it must be continuous. If a function is continuous, then it is not necessarily differentiable at C. And if a function is not continuous, then it is not differentiable. All right, so do you understand the difference here? You can have a function that's continuous at a point or in a section or for the whole thing, and then that function may or may not be differentiable. But if a function is differentiable, it has to be continuous. So you can't have differentiability without continuity, but you can have continuity without differentiability. Okay, so here's an example. These are some places where it's not differentiable. This first one is called a cusp. It's where two curves meet at a point. So we would say that this is not differentiable at x equals -3. The second one is called a corner. That's where two lines meet. So you've got two curves or two lines. So this one's not differentiable at, it looks like -1.5. And then this one has a vertical tangent line. So if you were to take the derivative, you get a vertical tangent line when the derivative is undefined, when you get like number over 0. Okay. So like f prime of that number would give you k over 0. So this one is not differentiable at -1. Okay. For piecewise functions, we had to check continuity. Usually at the point that there's a transition, you check to see if it's continuous at the transition. And by doing that, you would just plug into here and plug into here and make sure they're equal. Make sure the two y values from one direction and from the other direction meet at the same point, okay? And since a differentiable function has to also be continuous, you're still going to check to see if it's continuous first. After you check to see if it's continuous, then you can go on and check to see if it's differentiable. And to check differentiability, you're going to make sure, so in order for a function to be smooth at a point of transition, like from here to here, the slopes have to be the same at the point of intersection. And what do we use to figure out slope? Derivative, yeah. So to check for differentiability, you're going to check for continuity first. And if it's not continuous, then it cannot be differentiable. But if it is continuous, then it may or may not be differentiable. So you're going to check continuity, then you're going to check differentiability. So let me show you what that looks like. Okay, so to check for continuity, we're going to plug 2 in to both of the parts of our function to see if they touch, to see if they both get the same number. So technically what we're doing is the limit as x approaches 2 from the left, which is when x is less than 2, so the top one. We're going to plug in 2. I think that's 2. And then we're going to plug in the limit as x approaches 2 from the right. And that's also 2. So therefore this is continuous at x equals 2. So now we're going to check to see if it's differentiable. And to check that, we need the derivative. So we're going to take the derivative of the two parts of our function. And we'll plug 2 into that. So that means the slope, as the function is approaching 2, or as x approaches 2, the slope of the function is -2 from the left side. Because remember, this is two different functions meeting together. We know that they touch because it's continuous, but do they touch in a smooth way is what we're trying to say. So we take the derivative of the first one, plug in the 2, and then we need to take the derivative of the second part, which is 4 minus x. The derivative is -1. So that slope is not the same. So we would say this is not differentiable. And I'm going to show you what that looks like on the graph. So here's the picture of the graph. The blue one is as x approaches from the left, and the green one is as it approaches from the right. And the slopes are very close, like -2 and -1. Those are very close to the same slope. But you can tell that it doesn't smoothly connect. We could adjust the function and have a smooth connection, but I think there's an example that is differentiable that you could see that with. So, all right, so let's test number 2. We have to test for continuity first. So as x approaches -1 from the left, that would be the top equation, or the top rule. So -1 squared plus -1 minus 3. And then -1 from the right is the bottom rule. So -1 minus 4 is also -3. So it is continuous, meaning it'll meet together. And then we're going to test for differentiability. So we need the derivatives. So the derivative on the left would be 2x plus 1. So that's 2 times -1 plus 1. And then as x approaches -1 from the right, would just be -1. Okay, so it is differentiable. So let's see what that looks like on the graph. So we can see these are two different rules. One of them is a parabola. The x squared plus x minus 3 is a partial parabola. And then the -x minus 4 is a line. It's a linear function. So we know the math tells us that it's differentiable, that where it transitions from one rule to the other is a smooth transition. So this is what a function looks like that's differentiable at the transition point. We knew it was continuous. That means it meets, like it touches. But for it to be differentiable, it means that it's a smooth transition from one rule, the blue one, to the other rule, the green one. And for it to have a smooth transition, that means the slopes for both of these have to match each other. And the slopes were -1. If you're listening still, comment on Google Classroom your favorite breakfast food. Good job, everybody. So in the future, when you do a project on this, because you will, it's on page 97, you'll have to design a point that is both continuous and differentiable and prove that. Like you'll have to prove that the slope as it approaches on the left side is equal to the slope as it approaches on the right side. And the proof of that is this math that we just showed right here. That's how you prove it. Okay, so I want to do a little side-by-side of this function is differentiable. Why is it behind those arrows? That's weird. And then this function is not differentiable. So you can maybe see the difference. A little bit of a corner there.